So I wanted to go through our notes first. This is where we left off back here. So this was on the last test. So we did a derivation of arc length, the arc length formula. So we did all this. So this is all from the last test. So it might come up on the final, but not right now. So this part is all done. Okay, so then from there, we discussed the arc length function. So the function is defined basically as an integral. It's the sum of those little lengths, essentially. But t is arbitrary, so this t is an arbitrary value. So basically, don't worry about it too much. What you need to, this basically is used to define the unit tangent vector. And we showed, and you should be able to show as well, that it has length 1. So basically just take the magnitude of it, and then you can see that it has length 1. From there, we define the principal unit normal vector, which is basically taking the t prime and then dividing by its magnitude. So it is also a unit vector if you take its magnitude. Then the next thing we showed was that t and n are orthogonal or normal. So to do that, we set up this proof. So you should be familiar with this proof and how to do that. Excuse me. So it is done basically by this, the premise of it is by this formula, this theorem. Essentially that if the magnitude is constant, or the r of t is constant, then r prime is orthogonal to r and r prime. So these two here and here are orthogonal. So that's where it lies, because for t, since t has length 1, then its magnitude is constant. So then we can apply that formula that t and t prime are orthogonal. So when you divide by this non-zero constant magnitude t prime, that's not going to change anything. So this whole thing here is of course 0, and you're good to go. Okay. So know that, just be familiar with all that kind of stuff. Then we get to showing that that t and n lie in the same plane. So we look at t, we look at n, and this next definition, or not definition, or is it? We show that that they're in the same plane. That's a little later. That's this one. So this theorem states that. Before we talked about that, though, we looked at you need to have this concept. You need to have what a linear combination is. So the linear combination of two vectors, t and n, is basically a scalar multiple. These are the scalar multiples, and they're different. I just wrote it up on my notes. It can be different. Then it's a linear combination. So it's basically, it would be like these vectors. You have v and u. The linear combination might create w, but you can't make a vector that shoots like out of the screen, like up or something. Okay, so we defined that and used all that to look at, let's see. So that a of t lies in the same plane determined by t and n. So that's this proof. So you don't have to know this whole thing. Our format's going to be a little different anyway. But just be familiar with some of the steps that are taken here. Something maybe asked, but just so I want you to study it. So please study this proof and how you end up with your AT and AN. Those are called the tangential and normal components of acceleration. So those are your scalars of t and n that determine your vector a of t. So so know this basic curve, if that is r of t, like that. then as it's traced out, and this would be your ARP. Well, this B is supposed to be perpendicular. We'll talk about B later. So it's a linear combination of your N and T creates your A of T, like that. So be familiar with that. Be familiar with how to calculate these, AT and AN. This would be your evaluation formulas here. So you'll have access to all those formulas. So you'll be able to do those if asked. So just be able to calculate those. I don't do much with a binormal vector, but that's if you just cross T and N. And I believe you take its magnitude. I'm not sure about that actually, but don't worry about it too much. So T and N, you cross that and you get B. And that creates the T and B frame, which I showed you that picture that's traced out on a curve as it goes by. Okay, so that's just, so know some of the basics there. Let's move on to 3.4 on curvature. So 3.4 for curvature basically is this definition. So C is a smooth curve, and then notice it's R of S. So you have S here, not just T, where S is the arc length parameter. The curvature is given by dt ds. Now that kind of means nothing to us as it is. I mean, it's what it says. We know that. So it calculates the magnitude or the rate of change of the unit tangent vector with respect to arc length of S. So it depends what the arc length is and how it curves. So we would all agree that this curvature down here should be less than this curvature here. So that's the basic definition, and then from there you need to know just the basic calculation formulas like that. So be able to calculate curvature in both of these ways. It's not going to be all of these things, it'll be probably too much, but just be able to do that. Like this example we did in class, I don't have anything else on that. Let's see. This probably would take too long. This would be too long even for a take-home style test or how I'm going to do the testing. So, but this is good practice to find T, N, and your curvature for something like that. So if you can do those types of questions, you're good to go. Okay, we'll go on to the next chapter. We'll go ahead and do another video for that. See how this one went.